Now we are moving into the second topic, which is nothing but a diode. Under this, there is something called very important topic is p-n junction diode. p-n junction diode. p-n junction diode is something. This is a very important concept, guys, and as per the GATE exam, you will get many questions on this topic only. There are many other diodes called Zener diode, Varactor diode. There are so many. There are list. There are so many diodes available. But before moving into all these topics, let me give a brief idea about what is a diode and how. I mean, why it is actually needed and everything. So far, we have seen that both are linearly dependent. Like let's say resistor. A resistor is a linear dependent. If you take a voltage and current relationship, then you can see a linear behavior between voltage and current. Unlike the resistor, the diode, this is the symbol of a diode, guys. I hope you all guys are known, but just for the completion purpose, I'm just drawing this. This is the symbol of the diode, and this is not all linear, which is a non-linear. What I mean to say linear. If you want to draw a current and voltage graph between for a resistor, if we keep on increasing the voltage, the current will also increase by a same factor. And there is nothing like limit for this, and it will goes on. And the midpoint, let's say this is somewhere, if we take, and this is nothing but static resistance. But if we take 2 points and take the difference, and that is nothing but a dynamic resistance. This is a dynamic resistance. Taking the 2 points, this is a static. And static static resistance will keep on changing, guys, as we move. Let's say if we want to take a 2 points, let's say if this is a point, our point of interest. At this point, the static resistance is something. At this point also, the static resistance will change. Okay, but not a very big factor, but it will change a slightly more or less same. But the graph looks like this, so it is nothing but it uses a linear linear functionality. So if we take our mobiles or any electronic device that we are using today, there is always a potential available to all the elements, even if it is in standby mode. What I mean to say is, if you are not using your mobile, then it is in standby mode. Standby mode. At that time, the power consumption has to be zero, ideally, because you are not using it, isn't it? You are not using it. The power consumption has to be zero, ideally, but that is not the case in the real time. Real time, there must be some power distribution, and that must be as low as possible. For example, if you use a mobile for 1 hour and let's say it took from 70 percentage to 50 percentage, assuming, and another 1 hour you are not using the mobile, still it is on mode, which means it is a standby mode, and the battery becomes 50 to 35. This is not acceptable in a real time. Like, this is an acceptable case. Like, you are using 1 hour and the battery is consuming, and that is a bit acceptable condition, though the figure is 20% per hour, still it is okay, still it is okay. But you are not using here at this condition another hour, but it still dropped from 50 to 35. There is, you guys can easily observe using 20% drop, and here there is a 15% of drop, and this should not be the case. This has this has to limit by some factor, by using some approximation or some whatever. We have to do something, and we have to make it constant, like let's say 49. So that is the condition of diode. Why diode in that conditions? Let's say if you have a mobile, under that there are so many process. One processor will be there, one image processing will be there, one JPEG data compressions will be there, and MPEG JIT, MPEG compression. So many blocks are available within a mobile. But our point of interest is, if we are not using these three modules, then the power consumption has to be zero, because we should not apply any additional voltage. Let's say if we are applying a let's say zero voltage cannot be the possible case, and ideally it is not possible. So let's say we are applying some voltage. I mean, this is not our intention, but by default some voltage will apply. Let's say 0.5 voltage, which is a lesser 0.5. If this is the case, assuming there are two types of conditions. One, it is made up of resistor, and resistors are not practically used nowadays, but long years back, more than 35 years back, they are using resistors. After that, the diode replaced the resistors and all. Now so many diode updation will be there, and transistors and FET transistors, and there are so many things. But let's assume 30 years back, what is happening? The resistor, even if we apply this small voltage, and this device will turn on, this device will turn on, and this device will turn on, all the devices will turn on automatically. So the power consumption is 4 units, because of 4, obviously this is a used device, and 1 unit power consumption will be always be there. And then this is let's say there is a diode. Diode is something which will turn on after some voltage is crossed. Diode will turn on only after 0.7 volts and 0.8 volts, depending on the doping and there are so many factors which depends on that. But yeah, we will see that part a little later, but just keep it in mind, it will not turn on for the lower voltages, lower than 0.5. At this condition, only this is the unit which is using, so 1 unit only, because for these 3 small voltages the diode will not turn on, and these 3 devices will not contribute for the power dissipation. And this is the one of the major advantage of a diode. But 30, this is the case of 30 years back, not now. But there are specific applications where we still using diodes in our real-time applications as well, and we will see a bit later. But this is a case, like if we want to apply, or if you want something like for example, if you want to turn off the device by some voltage, I mean if the voltage crosses by below 0.5 volts, then your ultimate option will be a diode, okay? But nowadays transistors are widely used. 98% of the case transistors are used, okay? Now, how p-n junction will form and everything we will see in detail. Uh, Guys, listen carefully. This is a basic concepts. You have to know if you want to do it. If you want to understand the concepts of other devices and all other. If you go for transistors, if you go for any kind of transistors, it may be BJT, it may be FET, and the basic functionality. And the diode is a basic functionality, and you guys have to know. Okay, first of all, how diode will form. Let's say uh, I am using black color for just to indicate the things. Let's say this is a silicon. Let's say otherwise let's assume it to be a semiconductor. It may be germanium, it may be silicon. Okay, it may be germanium, it may be silicon. I'm assuming it to be a silicon. Let us assume it is a silicon. What you and this is an intrinsic semiconductor, not a P or N type. This is a pure semiconductor, which means it is an intrinsic semiconductor. And then you have to dope with the fifth group element here, where majority is holes. On the other side, third group elements are used for doping, which is nothing but P type. Yes, sorry, I'm the part here. Okay, we will get P type here and we will get a N type here because of I think I made a mistake again. We'll get a hole here, and so the majorities are holes and still it is valid. Yes. In a fifth type, we have a one more electron, so this is a fifth. Okay. Moreover, we'll get N and P on both sides. Mm, like we'll have a N here, we'll have a P here. Okay. Because of this, extra electron that we are doping in a fifth group element, we have a one electron extra. That means on this side there are electrons present. These are the electrons. In the same process, we'll have holes on the other side. I think in your theory classes, they might have explained holes on this side and electrons on right side, but this is pretty same process and there is nothing difference at all. Just the process I'm explaining, guys. Okay. Once, because this is the same process, there is electrons here and holes here. As we know, there is a concept called diffusion, and the electrons will try to diffuse from higher concentration to lower concentration. So the electrons will try to move from here to here, like this. The process is called diffusion. Again, the holes will move in this side because the same process will be applicable. Okay, in this case the hole concentration is high, in this case the electron concentration is high. Okay, the charge carriers will try to move from higher potential to lower potential, which is nothing but a lower concentration. At the junction, recombination takes place. Why just electrons and holes will try to recombine each other. At the center, we will have a neutral electrons, neutral ion, and which is a reason for our barrier creation, and this will create one barrier here. After some time, once the barrier has been created, the electron cannot move from this side to this side. In the same way, the hole cannot move from here to here. Initially it will move, but after some time it won't move. Okay, and this is about p-n junction diode. Once the barrier has been created, at the time we have our p-n junction will be ready. But keep it in mind, guys, we haven't applied any additional voltage so far. This is still in a natural conditions. So the process of moving of electrons is because of diffusion, which goes from higher concentration to lower concentration. Because of that, the barrier will be created. Um, they will recombine at the junction. Because of that, the barrier will be created. After that, the electrons and holes cannot move from one side to another side. Now, our this is how the p-n junction will be formed. Um, One thing I want to make you guys clear, somebody will say like if you take a p type one side and if you take a n type n type one side, then that will give us by just joining you will get a p-n junction diode. It is not the correct way of doing it. Initially you have to take one silicon bar and you have to dope with third group and fifth group elements on the both sides, so that the electrons and holes will try to move from either sides. At the junction, the barrier will be created after some time, and that is because of the recombination. Once the barrier is created, the electrons and holes cannot move from one side to another side, and this is a process of p-n junction formation, not this. The two n type and p type cannot be joined, and that is completely a big waste of time of process. That's not the case. Okay, we have seen that uh, we have seen that so far, how the p-n junction will be formed and everything. Within the p-n junction, because of that positive and negative at the barrier, we will have an electric field. As we know, electric field is something which just acts as a voltage supply. I mean, obviously it uses a voltage supply and all. There is some inbuilt electric field to the all the diodes, and if we apply a voltage more than that, then and then only we will get for moving movement of these electrons. Otherwise the electrons on holes will stay at the position, at that positions only. So far, we have seen how the PN junction will be formed and how there is something called input built-in potential or voltage, and sometimes we have to calculate this width of the barrier, and not every time the barrier is same. Barrier will be different from uh, case to case, like how much doping you are using, and there are so many factors which depends on. So there are certain formulas for that. I will share the PDF for you guys after the lesson. uh, you guys can understand, and we will solve the problems a little later. Okay, this is a PN junction diode. We have holes here, but at the time of explanation I said there are electrons, but the process are equally same. If the holes are here, the electrons are here, which means the P type on the left side and the N type is at the right side. Now we will see the biasing conditions. Whenever I say biasing, it means we have to apply an input voltage. So input voltage are of two types. One is forward biasing and the reverse biasing. Forward biasing is something that we apply a positive voltage to the P type, and negative will be connected to N type. I mean, we have a battery, and battery has two terminals, positive and negative, and the positive terminal is connected to the P type and negative terminal is connected to the N type. Once we do that, there is something called built-in voltage for this particular diode as well. We have to apply the voltage more than the electric field present in the inbuilt of that particular device. Then and then only the electrons can move, and I mean electrons or holes can move from one side to another side. So for example, if it is 0.5 volts is the input voltage, built-in voltage, then we have to apply something called 0.7 volts. Then and then only we will see the flow of electrons from holes and from one side to another side. Okay, we'll see how. And we are applying a positive supply of the battery to the P type, which means there are holes presented here, and the positive, if we apply a positive voltage to the holes, and it will repel each other, which means the holes try to move away from the positive voltage. In the same way, if we apply a negative voltage to the electrons, and electrons will try to repel to the ripple, and it will move in this direction. Because of this because of this we will get we will see the holes and electrons are moving, can cross the barrier because of this additional potential. Otherwise the barrier is strong in between P and N type, and electrons cannot move. But here in this particular case, we can see the electrons. These are the electrons. The electrons are will move in this direction, and we know that opposite to the electron the whole current flow, and this is the current flow direction. And there is a formula for that as well, and I will include the formula in the formula sheet, and we will see uh, we will solve the problems on that as well. This is the process of forward biasing, forward bias diode. Now because of that, we can see the IV characteristics I and V. From this graph itself, we can see this is something the input voltage has to cross. If we apply an input voltage below the input voltage, then we cannot see any current flow. We can see this is a 0, but once it crosses the input built-in voltage, the current will flow rapidly and it will increase a very huge, like within a second, within a 0.1 voltage change, the current will becomes very high. This is the characteristics of forward biasing of a particular diode. And there is some default values for the cut-in voltage. Whatever we have seen, this is called cut-in voltage. For silicon it is 0.7 ideally. For germanium it is very less, 0.2. Because of this cut-in voltage lower, the germanium cannot be used for most of the cases. This is the one of the reason why germanium is not used. Similarly, we will talk about the forward bias, reverse bias case. We have a holes here, we have a electrons here. If we apply a negative voltage to the p type, negative voltage to the p type and positive voltage to the n type, these holes, the majority holes will try to attract, because this is a negative terminal of the battery. Because of this, the holes will try to move in this direction, away from the barrier. In the same way, the positive is applied to the n-type semiconductor. The electrons will try to move in this direction. What we are seeing, the barrier will get increased after some time. Because all the holes are moving in the side and there will be no holes present, no hole will present after some time. So the width of the barrier will get increased if we increase the negative in the reverse bias. But in case of forward bias, the barrier will get decreased as we increase the forward input voltage in case of forward bias. The current flowing is very less and it is approximately 0, but we cannot take this approximation. There is still some current will flow, so in a reverse bias we will take in microamperes. In a forward bias we will take in milliamperes. The diode IV characteristics is different. Generally we will take the both same units, but in this case, for forward bias we have to take milliamperes in milliamperes, and for reverse bias we have to take in microamperes. Now coming to the characteristics of that reverse bias diode, we'll see a constant current, which is a very less, and it is in microamperes. Very less. We can neglect even sometimes. The interesting fact here is that for silicon it is in nano amperes. Nano is nothing but 10 power minus 9. For silicon it is 10 power minus 9 as well. But it cannot go beyond certain level, and will get damaged once it reaches certain point, and that certain point is nothing but a breakdown voltage in the reverse bias condition and all. We will see what this breakdown voltage and all. So far we have talked about PN junction diode and PN junction in forward bias and reverse bias and the IV characteristics. Now the next topic is how the PN junction diode can be replaced. How can we replace the PN junction diode in our problems? Let's say we have a diode with us. In an ideal case, I'm talking about forward biasing. Forward bias. The diode will be replaced by a straight line, which means the cutting voltage is zero. Ideally, the cutting voltage is zero, so we have to replace by a short circuit. But that is not a practical case. So we have something inbuilt voltage within a diode. So we will replace with a positive input voltage, which is nothing but V0 input built-in voltage. V0 is a built-in voltage. But in some case, very practical applications, we will replace our diode with a resistor in a series with the diode built-in voltage V0, and the resistance is forward resistance RF. This resistance is very small. But sometimes we have to include in the question. They may have given in the question like you take the forward bias resistance as RF, then we have to assume like this. The reason why I'm telling is that sometimes they will mention in a circuit as a diode and they will give the built-in voltage and the resistance and everything. We can replace with the normal input voltage and resistance. It will become a a simple circuit with a voltage and resistance and all, so that we can calculate it very easily using some of the theorems or some of the techniques based on network theory. Okay, that is the reason why we are using this analysis. And coming to the reverse bias, we have a diode in a reverse bias. Let's say it has to be open circuit, which means there is no current flow ideally, but in practical it becomes very less current. It will flow very less current. There is nothing like voltage in the reverse bias, so there is we can replace with a resistor in some cases, RR resistance in the reverse bias, and this is very high resistance. This is all about, guys. We will solve one problem now and then we will see. There is a one circuit. The input voltage is 30 volts. And the diode is connected and the resistance is connected, and the resistance value is 1 kilo ohms. We have to know the voltage difference between these two. V0 we have to find out, but nowhere in the question they have mentioned what is the semiconductor used and nothing else. So we assume it to be a ideal diode, and we have seen, because this is a P terminal and this is a N terminal, the positive is applied to the P terminal, which means it is in forward bias condition. Of course, the applied voltage is positive voltage, then only it is in forward bias. Forward bias. In the forward bias ideal condition, we will take it as a short circuit. Then there is no drop here, and the 30 voltage will exactly drop in between these 2 points, and V naught will exactly equals to 30 volts. Okay. In the same way, if there is some voltage and the yes, if the diode is in reverse bias and there is something called 1 kilo ohms, we have to find this voltage, and the applied voltage is 30 volts. Now in this particular problem, this is the N type and this is the P type. The 30 positive volt is applied to the N type, which means it is in reverse bias condition, and nowhere in the question they haven't mentioned about the metals used or reverse bias, anything, resistance and all. So we will assume it to be ideal, and we can replace it with open circuit. Under open circuit, the 30 volts will drop between these two only, and the voltage drop between the 1 ohm resistor is 0 volts. I hope these two problems are clear. I will take one more problem like this. Let us assume 30 voltage, 1 kilo ohm resistor. We have a diode here. Now we have to find the voltage. In this particular question, it is very simple question, and in the question they have mentioned that it is a silicon. This is a silicon metal, silicon semiconductor is used to manufacture the device. Guys, this is a 30 voltage and is applied. One thing is very sure that how much potential is applying is important. No, I mean, what is the positive supply or negative supply is applied is important. Even though the resistor is placed here, the positive voltage of 30 volts battery is directly connected to the P type of the diode. So it is in forward bias, and the resistance is not given for a forward bias. So we can replace this diode with a positive voltage, and the voltage is 0.7, because the input volt, the built-in voltage for silicon is 0.7. If it is a germanium, then the value becomes 0.2. If it is an ideal diode, no matter what, then the voltage is 0 volts. Okay, so the 0.7 voltage will drop is equal to V naught, and the rest of the voltage will drop here, which is 29.3 will drop in the 1 kilo ohm resistor. All the questions are pretty similar, guys, about the introduction of PN junction diode. I think this is all about the basics of PN junction diode. But there are some concepts called width of, the barrier width of the PN junction diode and the built-in voltage of the PN junction diode. These two are also important, and we will see in the next class.